Hi, my name is Casey Joyce, and this is my video analysis of Lab 1, an object moving in constant motion. For this lab, my object is a person walking in a straight line. On the tracker, I put the axis. The origin of the axis is right in the middle of the object, the person. By changing the axis, you control wherever the motion is. So if on mine, the origin is on the person, and they are walking from right to left on the video. So they are going towards the negative x-axis. If the origin was flipped, the numbers would stay the same, but the components of the vector of motion and the vector of velocity would be different. There'd be a 0 in the x value, and the number of the magnitude would be in the negative y direction, or positive, whatever way the axis was chosen to be. When I made my computational model, some of the numbers were different than in the actual model. I think this is because when you actually have a person walking, it's not exactly just an object controlled by a force. The person has free will to be able to slow down or speed up, so it was hard to keep them in actual constant motion. The numbers for both stayed pretty much the same in the beginning. The initial position was 0.0300. That was the initial position vector. The initial velocity vector was negative 2.45500. No, I'm sorry. That was the final position vector. It was negative 2.45500 meters, starting at 0.0300 meters. It went over 2.67 seconds, about 3 steps. It goes in the negative x direction, so that is why the position is negative. The object's initial velocity was calculated to be negative 1.81800 meters per second, which was used by using the two first data points. Because you're using the data points for your initial velocity, and that's the initial velocity I plugged in to the computational model in the programming, it shows that both the graphs started out very similar. Is when it went on, the computational model when it kept going, that's when the numbers started to change. The person must have slowed down, as the model showed that, because it goes up to negative 4.3 in the computational model, when in reality the person really only went to negative 2.455. The slope was the same, and it was a constant slope. The constant slope was due to the fact that the net force was 0. This is because there was once the initial push or pull, there was no other forces acting on the object. Therefore, it stays in constant velocity the entire time. It's hard because chose a person as my object, but different forces that would act on it if, for example, I pushed a ball would be the force of the Earth, which is the negative 9.8, which you find by multiplying the mass by the gravity constant. And the gravity constant would be negative 9.88. And then if you had an object like a ball, it would be an initial push from pushing the ball. And once that initial push of the force, the object will stay in motion until another force acts upon it. It will start decreasing, or deaccelerating, but the object would still keep going at a constant. When it was moving, it would be at a constant velocity. This was tried to be demonstrated by the person, but it didn't go exactly as that. For the origin, the way I placed it is once I placed it on the middle of the object, for the tracker device, I kept clicking on that same spot to keep the y value constant the entire way. It stayed at the y constant stayed at 0.04 the entire time. The slope of the graph is in the negative direction. On the actual graph from the tracker device in the filming, there is a weird spike at 1.2 due to a change. I must have clicked differently on the tracker or other personal errors. But the graph from the computational model is a perfect linear graph, as it should be, with a constant velocity, and then going in a negative direction because the object is moving in the negative x direction. That is all the analysis I did, and thank you.